Thank you, Kilian. Okay, let us start. So yesterday we discussed about skew Brownian motion, Walsh Brownian motion, and today I would like to construct something where, okay, the process we called the skew stable process, but the main question is, what is the natural definition? What is the natural analog of a skew Brownian motion? The first characterization of a skew Brownian motion was done by Walsh, for example, describe all diffusions. That means continuous strong Markov processes such that its absolute value is a reflecting Brownian motion. Walsh proved that the only possibility is the following: X should be a skew Brownian motion. And there are a lot of approaches how to define. The first one was given by Ita and Makin in their book. So they took reflected Brownian motion and then flipped, okay, and flipped excursions with probabilities P and 1 minus P. Well, you can write transition probability density function, so another definition. Portenko characterized the skew Brownian motion in terms of stochastic differential equations, where he gave some meaning to the delta function of 0. Well, in a modern approach, this is nothing but the local time at 0. And Harris and Shep in 1981 proved that the corresponding SD has a unique strong solution where L is a symmetric local time in 0. And Walsh characterized skew Brownian motion via martingale probe. Another approach by Harris and Shep was perturbation approach. We take symmetric random walk plus and minus ones with probability 1/2, and then we perturb transition probabilities at 0. So when the process hits 0, you exit up with probability P, and exit down with probability Q is 1 minus P. And then consider Donskir's scaling limit, and it can be shown that the limit is a skew Brownian motion where this permeability parameter is P minus Q. Well, you can consider, for example, perturbations of a Brownian motion and construct the following process. You hit 0, then you exit from 0, and the exit is, say, zeta 1/1. Again, Brownian motion, independent of the past. You hit 0 and then jump. And this is zeta 2/n, where zeta 1, zeta 2, zeta 3 are IID with finite mean. And it can be shown that the limit is a skew Brownian motion. The limit is a skew Brownian motion where permeability parameter is expectation of zeta divided by expectation of absolute value of zeta. By the way, yesterday we discussed entrance and exit random walks. So here exit random walk, so it's just 0, 0, 0. And my formula was you have to, and entrance is zeta 1/n, zeta 2/n, zeta 3/n, and my yesterday formulas is just this. Okay, and now I would like to discuss skew processes, skew stable Lévy processes. But the first step, okay, let me just recall you that I consider symmetric alpha stable Lévy process, and I would like to find natural analog of the skew Brownian motion. But at first, let us discuss how we can describe Markov processes. Well, we may write down transition probabilities like Gaussian or stable, something like this, or write formula like a formula for skew Brownian motion. Well, if you have this, you can construct semigroups, generators. If you have generator, then you can write down Kolmogorov forward, backward equations. Resolvents describe generator, and if you know the resolvent, then you can construct theoretically a Markov process. There are also other approaches. All of them are complementary. For example, when you use this excursion theorem, you understand what is behavior of the process. For example, you take some, so it's like constructive method. You take excursions, then flip them or leave it as they were, and you understand, okay, you get continuous processes. You immediately understand properties of paths, say some Hausdorff dimensions or Lipschitz or Hölder continuity and so on and so forth. Actually, stochastic differential equations is, in some sense, is also constructive approach. You have a noise, Brownian motion, and solution is, okay, strong solution is a function of the noise. Sometimes martingale problem is very convenient to prove limit theorems. And now let's start. And let's start with Ito and Makin idea. And we take Lévy alpha stable process with alpha between 1 and 2. Yes, today I consider only this case. And in this case, the process U alpha hits 0 with probability 1. Hits 0 with probability 1. Unfortunately, excursions and trajectories of U alpha are discontinuous. And when you hit 0, you cannot say that you don't jump into 0. There are infinite number of crossings before hitting and after hitting. So idea with changing a sign of excursion fails. Okay, another approach. You can write the density. Well, assume that phi alpha t is a density of these. You can consider this function. It can be seen that it is a density. You have to use unimodality of the density of this density, and it's not so difficult to check that Kolmogorov-Chapman equation is satisfied. So there is a Markov process. Well, is it a natural analog of a skew Brownian motion? Well, I want to find a process such that its behavior outside of 0 coincides with behavior of U alpha. But if you write the generator, actually it was done by Perturbed, then you see that jump intensity is different. So maybe this is not good idea. However, there is a Markov process. There is martingale characterization, and moreover, you can get this process by subordinated Brownian motion. Okay, the next approach. Okay, diffusions with generalized drift. And let me tell you idea of Pilipenko. Okay, he studied diffusions, multidimensional diffusions with semi-permeable membranes. Okay, with semi-permeable membrane, so S. like multidimensional analog of skew Brownian motion. And he said, okay, what does it mean that you have membrane? That you have something like delta function drift, some generalized drift. Well, then he said, I want to construct a semigroup as a perturbation of Brownian semigroup. So you have a Brownian semigroup, Brownian motion semigroup. Well, detail, she write formally some equation, Rn, well-known equation. Okay. So he wants to construct semigroups. Assume that Gpxy is a density of a Brownian motion, and this corresponds to this. And Pilipenko tried to find this G as some perturbation of this G plus integral from 0 to t ds integral over Rn G e minus s x z, then gradient of G s z y. Well, if the drift is the usual function, then you have to write a of z dz, and let us denote this function by d. And then he said, okay, now formally plug here delta function, generalized function. Okay, this function denoted by fsz. When you plug delta function, then he said y0, differentiate this with respect to the second coordinate. Then he obtained equation for this v and say, well, let's consider solve for v, found v. And then he said, okay, you have g, t, x, y, and there are few questions. First, is it transition probability of Markov semigroup? And the answer was yes. It is non-negative. Integral is 1. Kolmogorov-Chapman is satisfied. Then, what is the process? It's a Markov process. He calculated, say, diffusion characteristics. In diffusion characteristic, he proved that this process is a sum of, say, Brownian motion plus some additive functional that and this additive functional may changing only when the process hits the surface. And then he characterized this additive functional in some sense like a local time function. It was important that when he solved his equations, that he used result dealing with the jump of the normal derivative over a single layer potential. Unfortunately, there is no similar result for alpha stable processes. However, he found the analog and did all this stuff, and it appears okay, he got a semigroup, but this semigroup was not positive. So he got, so integral is 1, integral was 1, but it was positive and negative parts. And it's a question, what does it mean? Like negative and negative mass or dark mass, I don't know. Another idea of Partenko was this: let's approximate delta function in the following way and try to pass to a limit. And as we discussed it yesterday, the result is skew Brownian motion, but this parameter is not alpha times delta function, but hyperbolic tangents of alpha. Okay, another approach, stochastic differential equations. Let's try to write stochastic differential equation with U alpha stable process and the local time of an unknown process. So how did Harrison and Shep prove the result? They used Tanaka formula, make some transformation of initial SDE, then they got equation without the local time. And this function sigma was, okay, one constant for x positive, another constant for x negative, and these two constants were positive, and then he applied Nakao theorem. And Nakao theorem works only in the case when the noise is a Brownian motion. So we don't know how to do if the noise is alpha stable. Okay, and martingale problem, but if you don't have a problem, if you don't have a process, you cannot write martingale problem. Well, and now let's try to do perturbations. Yes. Mm-hmm.
Construct the mesh, which is
no.
What's called Markov theorem.
No, Partenko did not. But this is interesting question.
You might, at the physical level, rigor, perhaps, there may be some field.
Well, and now let's try to apply perturbations. So let's construct the following process. Okay, these results are our joint work with Alex. I forget to mention with Alex Iksanov. Okay.
Not positive transition function. It emerges in what dimension?
In Rn.
For any n.
For any n, yes. For any n, and membrane was a plane, I think.
So for n equal to 1, the membrane was a line.
A point, yes, a point. So let's define the following process. At the beginning, alpha stable. Okay, I make a quotidious picture. Sorry about this. I have to write jumps. When you hit, you exit, and assume that exits are IID and smaller and smaller, and then we send n to infinity and try to find the limit. Well, this process is a sum of U alpha, so increments of the noise, plus exits. So this is a fixed process. So if the limit exists, then the limit of this sum should exist. And it's natural to assume, okay, averages converge. so it's natural to assume that either expectation of zeta is finite, or that zeta belongs to the domain of attraction of a stable law. And the first, okay, in the case when alpha is 2, in a limit, we get skew Brownian motion. Here, we have a difference. If expectation is finite, or beta is large enough, then perturbations have no effect in a limit. So the limit is just initial value plus noise. So this is the first part of theorem. The more interesting will be when beta is less than alpha minus 1. Okay, and the proof is the following. Well, we have to control the number, the sum of jumps. Well, if we delete this first excursion, okay, then we see that these intervals are IID. And okay, we have some we use some self-similarity property. For example, if you start from X and want to know the distribution of the heating time, and if you start from 1, then you have this equality in distribution. It's known, the distribution of sigma 1. It's known that its Laplace transform has the following asymptotics. So sigma 1 belongs to the domain of attraction of a stable law with this parameter. And okay, that also belongs to domain of attraction of beta stable law. What does it mean? That sums of zeta k over n, okay, integer part, converges to a stable law with parameter beta. So if you take essentially smaller number, then the result is 0. If larger, then infinity. Well, take point T, and you have some IIDs with nice scaling property. So you can multiply by n and ask the same question, but with point n to the power alpha times t. And well, if you make some comparisons, then you can see that the number of returns has this order, and this is smaller, much smaller than n to the power beta if beta is greater than alpha minus 1. So the corresponding sum converges to 0. And another case, if beta is between 0 and alpha minus 1, so then there is a limit, and we call this limit a skew symmetric Lévy process. It can be proved that this sequence converges to a Markov process with certain resolvent, where the alpha is the resolvent of symmetric alpha stable process that is skewed at 0. And this eta is this measure. Beta is beta, okay, from the limit of this. And C plus, C minus are positive and negative. It describes the positive and negative tails of this distribution. Okay, how to prove this result? Let me mention one theorem that if you have a sequence of failure processes, then, and assume that initial conditions are convergent, then you have convergence in distribution in Skorokhod space if and only if the semigroups locally uniformly convergent or resolvents. For example, for semigroups, the good reference is Etier and Tort's book, and equivalence of convergence of semigroups and resolvents is a result from functional analysis, from just general semigroup theory. So let us calculate resolvents and try to pass to a limit. Well, one small remark. This process with perturbation, to be honest, it does not visit zero. It touch zero and exit. So it spends zero time at zero. So originally we did the following thing. We hit zero, then spend here very small exponential time, and then exit. Then the phase space, the state space are same. However, there is a generalization of this result. I also got it from Etienne Kort's book when state space are different. For example, the state space for this problem is R without zero. And to prove weak convergence, you have to prove weak convergence of resolvents, uniform convergence of resolvents, and En now is just R without zero. And I would like to say that everything is computable. All resolvents of our process, and this is just calculation, well-known calculations, how to calculate resolvent of the process, some relations. So our main objects are the following. Okay, semigroups. So X is just general strong Markov process. Resolvent. And filled semigroup. Okay, filled at zero. So this is expectation of f of x times indicator that the moment of hitting zero is greater than. And resolvent of the filled semigroup, which is expectation. Okay, I can place expectation here. Integral from 0 to sigma f of x of t. Well, and sometimes you know this or this, and let me describe a relation between a resolvent of non-killed semigroup and a resolvent of killed semigroup. We start from X. This is sigma 0. And the resolvent we split integral like a sum of two terms, the first part and the second part. And the first integral, expectation of the first integral is resolvent of the Kilt semigroup. And at this point, you start from the very beginning. You apply strong Markov property, you start from zero. And well, by strong Markov property, you get this. Actually, if you know the semigroup of the Kilt semigroup, then you know this. Indeed, if you plug here 1, what will you get of 1 of x is expectation of integral. Oh, I forgot, sorry, I forgot e to the power minus lambda t. Minus lambda t dt is expectation of 1 minus e to the power minus lambda sigma 0 over lambda. So 1 over lambda minus 1 over lambda. Okay, times this. So if you know d, then you can calculate. Then you can calculate this. Well, and then let's calculate resolvent of our perturbed process. And again, so we have the first part, which is like Kilt semigroup, where you kill your alpha stable process, plus other part, but then you start from the point zeta over n. So you get this expression, then you plug zeta over n here and here. Then you calculate expectation. And then you see, you get equation for expectation of resolvent taken at the point zeta over n. So the answer is this. The answer is this. And okay, the answer. So resolvent of our, I have to write here index n, of our perturbed process has this form. And to find the limit of resolvent, we have to pass to a limit here, because you see, this is constant. This is constant. These parts are independent of n. So you only have to pass to a limit. And what is this? What is this? So let f be a distribution of zeta. And zeta belongs to domain of zeta belongs to domain of attraction of stable law. So this means that there are that constants c plus minus are limits as y tends to plus infinity of probability that yes, zeta greater than 1 over zeta greater than, okay, c plus is this. And it's known that these tails are regularly varying functions. So if you consider this nx and divide by this, then and send n to infinity, then you obtain for positive x c plus over x to the power beta, and if you consider less than minus n over absolute of value of x, then you get c minus divided by x to the power beta. So we divide this expression by this, and we see that in some sense, measure in the numerator converges to this measure, but this measure is infinity. The total mass is infinity. There is no problem when x is large, but there is some problem if x is small, when x is in a neighborhood of 0. So you have to control asymptotics of this in the neighborhood of 0, and it's known. And okay, and this is some problem. Well, how to pass to a limit, but at least this is a problem of analysis which is not so hard. Well, this is just some calculations. Okay, as I said. Yeah, sorry, one. No. Okay, this is some calculations. And another question is, well, you have the resolvent, but what is the behavior of the process? Can you write stochastic differential equation or something else? And the answer is yes. It can be proved that this process is a weak solution to the following stochastic differential equation, where U alpha is symmetric alpha stable process, U beta is a stable Lévy process with the following Lévy measure, with concrete constant. This process has zero sojourn at 0, and this Lx0 is a local time of this unknown process at 0. For example, for skew Brownian motion, you don't have this part. You have just gamma times, you have to replace U of L by gamma times T. Gamma times T, and when you plug L0, you get this. You get this. Well, and what is the local time? What is the local time? The short definition, what is the Blumenthal-Gettur local time? You have a strong mark, you have a failure process that visits 0 with probability 1, and the definition is this. A continuous additive function L is called the local time at 0 if its Laplace expectation of its Laplace transform is this. Well, you may ask the question, what does it mean? Why this? It's like definition of a Brownian motion, a Gaussian process, 0 mean and covariance S minimum T. When I was a student and I looked at this as the definition, I was wondering why minimum, why not maximum, why not sum, why this? Well, this is easy to understand. This is easy to understand. Well, usually the local time is a continuous additive functional that may grow only when the process hits 0. Let's try to calculate integral of e to the minus t dlt. This is sigma, this is sigma 0. Okay, here the process is not 0. So the local time is 0. So this integral is equal to the integral from sigma to infinity. And you take the expectation, you apply strong Markov property, and you see that this integral is integral after some change of variable, change of variables of minus sigma times expectation of this integral when you start from 0. And this is independent of x. And okay, we say that L is canonical local time if this integral is 1. Well, the question is, and this is not trivial result, that the local time exists, that this defines some additive functional that is supported at 0. Yeah. So this is a very hard work. Well, but okay, now I would like to explain the notion of a local time from the point of view of eta excursion theorem. And just a few words about eta excursions. Well, assume that you have a strong Markov process that visits 0 with probability 1. Well, assume that and assume that we start from 0. So excursion is a part between two zeros. Well, usually when you hit 0, there are infinite number of excursion in the neighborhood of this point, but I cannot make a picture. I would like just to explain ethos idea. And now this process is the following. We take excursions and stick them and glue them together. Well, in some sense, the distribution of these excursions should be independent, in some sense. And eta did the following procedure. Okay, let's consider a Poisson point measure in the space S, so time, times Skorokhod space. So every point S u is a pair, time and excursion. And I will say that excursion is the part, okay, sometimes excursion may start not from 0, but end at 0, okay. So this is a function. So time is that direction. Yes, yeah. So I have to make maybe this picture. So this is a function. And then we go from the left to the right. And okay, we get the first point, draw this excursion. We hit this excursion and we make the picture, and so on and so forth. Well, if intensity is finite, then there is no problem. But in the most interesting cases, intensity is sigma finite. So you have to do it accurately. And the rigorous definition, well, is given. Moreover, well, you have this excursion measure, so intensity measure here. Intensity measure here, you measure lengths of excursions, plus maybe some delay at 0, some ms, and make eta construction. Sometimes result is a Markov process. I never, well, I didn't tell you what about intensity here. So you cannot take it arbitrary. If you wish to get Markov process, there should be some restriction. And well, it should be in some sense compatible with the minimal semigroup. This property is like Markov property, but the total mass may be not one. And under some natural assumptions, there is one-to-one correspondence between this measure, excursion measure, and Markov processes. Well, natural means that, well, you hit 0, that if you are close to 0, then the time when you hit is small. Of hitting is small. And well, if that parameter m is 0, then you spend 0 time at 0. And the question is, well, theory is good. We have a Markov process. We have to. Is it possible to find this excursion measure? Well, if the measure is finite, and as I told you, you have compatibility conditions, then this measure can be calculated like by Ionescu-2 theorem, like arguments for Markov processes. You have transition semi-group, and that's all. And but in general case, so if the process exit from 0 by a jump, then this measure can be described as false. Yes, you start from this point and wait. It will be finite measure and wait before you hit 0. But for Brownian motion, this is not the case, and there is one equivalent description of this excursion measure. Let's consider the following probability. This probability that these excursions live more than t units of time. And okay, this is the distribution of excursion at the moment of t if this excursion doesn't hit 0 before t. Yes.
For Brownian,
yes.
This intensity measure.
Infinity.
Space,
yes.
is it known?
Yes.
How can you describe it?
Probably via this theta t. Yes. So this is infinite measure, sigma finite measure, defined on excursions. So if you take t and take only excursions that do not hit 0 before t, then you start from some measure called, well, this measure is known, and then you just write Brownian motion before you hit 0 and then stop. And then you have to send t to 0, and you'll have more and more excursions. Yes, and the question is how to pass to a limit, to the limit. Yes. Of this theta t? Well, I'm sorry, the answer is known, I cannot write. Maybe, Chris, maybe you know. Yeah. Yes, they're compared. No. What is theta t dx? I don't remember. So it's like constant divided by t, probably.
Oh,
Yeah. You have compatibility, but I don't know what are arguments. Well, it can be proved that the measure exists, but you have compatible sequence of measures, and you have to pass to a limit and to extend these measures to the set of all excursions, to the whole space, And in our case, this entrance measure can be.
Can you attach a name?
I think Ito. Maybe Ito. Because Ito proposed to glue these excursions together. Yeah, and in the case of our process, this entrance law or this measure can be described easily. You take the measure. Maybe I have. Okay, you take this measure on the line, infinite measure, And then you start Brownian motion from X before you hit 0. So this is excursion. This is intense excursion measure. Yes, but the measure eta is infinite. The measure eta is infinite. And the last question is this. Well, you have this equation. You have concrete constant. And let me recall you stochastic differential equation for the skew Brownian motion. What is gamma? So here, everything is fixed. Everything is fixed. In our limit, everything is fixed. Is there analog of gamma between 0 and 1 or -1 and 1? And the answer is yes. Well, the question, assume that you place here some gamma that is less than 1. Is there a solution? And if there is a solution, so what is this? And the answer is the following. This equation has a unique weak solution. Well, we study only failure processes in a class of failure process. And this excursion measure is a mixture. The first part is our jump part, jump exit. And the second part is in excursion measure for U alpha itself, So if you write this equation, then excursions of the process are the following. Okay, sometimes you have continuous exit from 0, continuous but jump. Sometimes you exit from certain intensity. Well, and you have these and these excursions. So you have different exits from 0. So you have just to mix trajectories of U alpha itself and trajectories of that skew alpha process. And that's all. Thank you for your attention.
The machinery to compute the moment the time for a stable few process in terms of scale function.
No, there is no scale function. When you okay. For the expectation. Well, I don't know. We invented this process just a few years ago, and I really don't know. Maybe you can write some equations for prelimit processes and pass to a limit. No, for scale function, no. But I don't know. There is no scale function for alpha student. Yeah, scale function is for continuous or for processes that do not have negative jumps, for example. Okay. Yes. So Portenko developed the theorem when you have a surface. Maybe the reference is to Portenko and his colleague and former PhD student Kopytko. So they construct diffusion with some drift, say, positive side, negative side. So this is drift coefficient. They should be, I think, Hölder continuous. sigma matrices plus minus x also, well, uniformly non-degenerate plus some Hölder conditions, like in classical theory. So these A and sigma may have a jump at this surface. You have some vector field here such that, well, projection on the normal is 1. This is just normalization. And yeah, like oblique, yes, and some permeability parameter gamma that may depend on a point. And they constructed a semigroup, and they represent the process. Okay, not Kopytka, but Portenko. This guy studied semigroups. He doesn't have probabilistic interpretation, but Portenko did a lot in this direction. So X is a sum. Integral part, so x0 plus axs ds plus integral from 0 to t sigma xs dws. So everything is multidimensional. Well, sigma is sigma plus here and there. Spend 0 time at the membrane and plus some additive function of bounded variation continues. And this additive functional is a limit as epsilon tends to 0, 1 over epsilon, integral from 0 to t, some approximation of this generalized function, ds. And these, okay, there are concrete rigorous statement. What is the function f epsilon? What is the convergence? And this additive functional cannot change if you are here or here. So it may change only when you hit this this surface. Well, and conditions are more or less reasonable, some Hölder continuity, something like this. This parameter gamma should be between -1 and 1 as for classical case. At the beginning, this gamma was conormal vector, and sigma was just sigma here and there. But then some generalization for sigma plus and sigma minus. Yeah. And I don't know, is there a strong solution? So this is a big question. I don't know about strong, because one-dimensional case, you apply Nakao theorem. There is no analog in multi-dimensional case. Well, for some simple cases, it is not difficult to show that sometimes there is a strong solution, but in general case, I don't know.
But the weak solution is unique.
The statement is this: weak solution is unique in the class of processes such that they transition probability density functions satisfy some Gaussian estimates from above.
Yeah. And this sequence epsilon, is it a standard sequence, or it depends on the process?
F epsilon? No, it depends.
Or it depends on the geometry.
Let me say. Well, in some sense, it depends on the process. Okay, let me write. Assume that you have a nice Markov process, and A of t is a continuous additive functional, one-dimensional case, but arbitrary state space. This functional is determined uniquely if you know so-called characteristics of this, or Laplace transform. Well, I follow the Dinkin's book. Well, if this functional is continuous in x, t, and t, then it's called W functional. And it is known that if you have uniform, probably, convergence of these characteristics in t and x, then you have convergence of additive functionals in LP. So Portenko used some concrete approximation, but but this characteristic is computable. Okay, let's calculate. Okay, the characteristic f, okay, g epsilon. The characteristic is epsilon is integral from 0 to t g epsilon of y n pt ptx y dy ds. So you have this characteristic. In Portenko proved that in some sense this converges to this generalized function. But if you have nice properties of pt, and he proved this, then you can take another approximation of this delta function. Just apply this theorem and prove that the limit characteristic is what you need. For example, in one-dimensional case, you can approximate symmetric local time by the following sequence, but you also can take Gaussian approximation, and you'll have the same answer. For example, Harrison and Shep used this approximation, and Portenko used Gaussian. So this is the only difference. But it was convenient to select G sub epsilon in certain way in Portenko works, but it is not really a problem to use another approximating sequence. Mm-hmm.
For me, one thing. My guess is that
yes, exactly. You're right. Yes. Yes, you're absolutely right. Yes, there is one-to-one correspondence. Well, to introduce Revos measure and this correspondence, I have to add some words, and this way is shorter. Yes, I agree with you. Yes, and you need some results that if Revos measures converge in some sense, then you have convergence of additive functionals. Yeah, here the Revos measure has just this density.
any last question?